The Midrex process was developed by the Surface Combustion Division of Midland Ross Corporation in the mid-60s. The Midrex division became a subsidiary of Corf Industries in 1964. Midrex was subsequently acquired by Koba Steel Ltd. In 1983. The first commercial Midrex plant was installed near Portland, Oregon, and started production in 1969. The plant included two shaft reduction furnaces of 3.4 meters or 11.2 feet inside diameter and had a total capacity of 300,000 tons per year. The average energy consumption of this early plant was approximately 15 joules per ton of direct reduced iron. Many difficult engineering and operating problems were solved during the first several years of operation of this plant that contributed significantly to the design, construction, and operation of larger Midrex plants throughout the world. The largest module has a capacity of 1.2 million tons per year. The reduction shaft in this plant has an inside diameter of 6.65 meters or 21.8 feet. The Midrex direct reduction flowsheet is shown in figure. The main components of the process are the shaft furnace, the gas reformer, and the cooling gas system. The temperature and composition of the gas to the shaft furnace is controlled to maintain optimum bed temperature for reduction, degree of metallization, carbonization level, and efficient utilization of the reducing gas. The direct reduction furnace is a steel vessel with an internal refractory lining in the reduction zone. The solids flow continuously into the top of the furnace through seal legs. The reduction furnace is designed for uniform movement of the burden through the furnace. The cooled DRI, direct reduction iron, is continuously discharged through seal legs at the bottom of the furnace. Inert gas is injected into the seal legs to prevent escape of process gases. The DRI is screened to remove fines that are usually bracketed to provide a usable DRI product. Reducing gas, approximately 95% of hydrogen MCO, enters the furnace through a bustle pipe and ports located at the bottom of the reduction zone at 760 or 927 degrees Celsius and flows counter-current to the descending solids. The shaft of gas, containing approximately 70% of CO plus hydrogen, flows from the shaft outlet to a scrubber, where it is cooled and scrubbed to remove dust. Most of the top gas is recompressed, enriched with natural gas, preheated to approximately 400 degrees Celsius, and piped into the reformer tubes, where it is reformed to carbon monoxide and hydrogen. The hot reformed gas, containing approximately 95% of CO plus hydrogen, is then recycled to the shaft. The excess top gas provides fuel for the reformer. Hot flue gas from the reformer is used in the heat recuperators to reheat combustion air for the reformer burners and to preheat the process gas before reforming. The addition of heat recuperators to these gas streams has enhanced process efficiently, helping to decrease annual fuel usage. Cooling gases flow counter-current to the burden in the cooling zone of the shaft. The gas then leaves at the top of the cooling zone, flows through the cooling gas scrubber, and is compressed, passed through a demister, and recycled. In an alternative flow sheet, shaft of gas is used for cooling prior to introduction into the reformer. The DRI, direct reduced iron, absorbs sulfur in the top gas and prevents sulfur poisoning of the catalyst.